The vast distances between objects in our solar system can be overwhelming, and the speed at which information travels can be surprisingly slow. Let's dive into the details of why a simple text message to Neptune from Earth can take over 4 hours, even when traveling at the speed of light. The distance between Earth and Neptune. The 8th planet in our solar system, Neptune, is approximately 4.5 billion kilometers, 2.8 billion miles, away from Earth. This enormous distance is a significant factor in the time it takes for a signal to travel between the two planets. The speed of light is even mind-boggling in cosmic calculations. The speed of light is the fastest speed at which any object or information can travel in a vacuum, which is approximately 219,792 kilometers per second, which is approximately 186,282 miles per second. This speed is a fundamental constant of the universe and is denoted by the letter c. To calculate the time delay between sending a signal from Earth and receiving it on Neptune, we can use the formula time delay equals distance divided by speed. By plugging in the numbers, we get time delay equals 4.5 billion kilometers, which is the distance to Neptune divided by 299,792 kilometers ines, which is the speed of light. This gives us 15,039 seconds, or approximately 4.17 hours. So even at the speed of light, a simple text message to Neptune from Earth takes over 4 hours to arrive. This time delay is often referred to as the one-way light time, or OWLT. Why can't we send signals faster? You might wonder why we can't send signals faster than the speed of light. The answer lies in the fundamental laws of physics, particularly Einstein's theory of special relativity. According to this theory, nothing can reach or exceed the speed of light in a vacuum. This speed limit is a universal constraint that applies to all objects and information. Attempting to send a signal faster than light would require an object to have an infinite amount of energy, which is impossible. Even if we could somehow manage to accelerate an object to relativistic speeds, the energy required to do so would be enormous, and the object would likely be destroyed by the intense forces involved. Implications for space communication. The time delay between Earth and Neptune has significant implications for space communication. For example, 1. Delayed responses. If we send a message to a spacecraft near Neptune, it will take over 4 hours for the message to arrive. The spacecraft will then respond, but its response will take another 4 hours to reach us. This means that a simple conversation between Earth and a Neptune-bound spacecraft could take over 8 hours to complete. 1. Autonomous decision-making. Due to the time delay, spacecraft often need to be designed to make autonomous decisions without relying on real-time communication with Earth. This requires sophisticated onboard systems and pre-programmed instructions. 1. Mission planning. Space agencies and mission planners must carefully consider the time delay when designing missions to distant planets. This includes accounting for the delay in communication, as well as the time it takes for spacecraft to travel between planets. The time delay between Earth and Neptune is a remarkable example of the vast scales involved in our solar system. Even at the speed of light, communication between the two planets takes over 4 hours, which has significant implications for space exploration and communication. As we continue to push the boundaries of space travel and communication, understanding these fundamental limitations will be essential for designing and executing successful missions to the outer reaches of our solar system. While there are no current missions specifically planned to send a human crew to Neptune, scientists and space agencies are actively exploring the outer solar system, including Neptune and its moons, using robotic spacecraft and telescopes. Here are some efforts being made to explore and study Neptune. Current and future missions. 1. Voyager. 2. Launched in 1977. Voyager 2 is the only spacecraft that has visited Neptune, flying by the planet in 1989. Although it's no longer actively exploring Neptune, it continues to send back data from the outer reaches of the solar system. 1. New Horizons. Launched in 2006, New Horizons flew by Pluto in 2015 and is now exploring the Kuiper Belt, a region of icy bodies beyond Neptune. While not specifically targeting Neptune, the mission has provided valuable insights into the outer solar system. 1. Europa Clipper. Scheduled to launch in the mid-2020s, the Europa Clipper mission will explore Jupiter's moon Europa, which is thought to have a subsurface ocean. Although not directly related to Neptune, the mission will help scientists understand the habitability of icy moons in the outer solar system. 1. Trident. A proposed mission to explore Neptune's moon Triton. Trident is currently in the concept phase. The mission would study Triton's subsurface ocean, geology, and potential habitability. Future concepts and proposals. 1. Neptune Orbiter. A proposed mission concept that would send a spacecraft to orbit Neptune, studying the planet's atmosphere, magnetosphere, and moons. 1. Neptune Flyby. A concept for a flyby mission that would send a spacecraft to explore Neptune's atmosphere, magnetosphere, and moons, potentially including a landing on Triton. 1. Interstellar Probe. A proposed mission that would explore the outer reaches of the solar system and beyond, potentially including a flyby of Neptune. Technological advancements. 1. Nuclear power. Scientists are developing new nuclear power sources, such as the Kilopower project, which could enable longer duration missions to the outer solar system. 1. Advanced propulsion. Researchers are exploring new propulsion technologies, like advanced ion engines, Hall effect thrusters, and light sails, which could potentially reduce travel times to Neptune. 1. Hibernation technologies. Scientists are developing hibernation technologies that would allow spacecraft to survive the long journey to Neptune by reducing power consumption and minimizing the risk of system failure. Challenges and considerations. 1. Distance and travel time. The average distance from Earth to Neptune is about 4.5 billion kilometers, 2.8 billion miles, making it a significant challenge to design a mission that can travel such a vast distance. 1. Radiation and harsh environment. The outer solar system is a hostile environment, with high levels of radiation and extreme temperatures, which can damage spacecraft electronics and affect their performance. 1. Communication. The time delay between Earth and Neptune, as mentioned earlier, poses significant challenges for communication, making it difficult to control and receive data from spacecraft in real time. While these efforts are aimed at exploring and studying Neptune, sending humans to the planet is still largely speculative at this point. However, as technology advances and our understanding of the outer solar system grows, we may see more ambitious plans for human exploration of Neptune and its moons in the future. Communication between Earth and other planets or cosmic bodies is a complex process that involves various technologies and strategies. Here's an overview of how it works. Methods of communication. Radio waves. Radio waves are used to transmit data between spacecraft and Earth. Radio waves can travel long distances through space and can penetrate the Earth's atmosphere. Deep Space Network, DSN. The DSN is a system of antennas around the world that communicate with spacecraft and other celestial bodies. The DSN uses large antennas to transmit and receive signals. Laser communication. Laser communication systems use light to transmit data. These systems can offer higher data rates than radio waves, but require more precise aiming and are affected by atmospheric interference. Challenges. 1. Distance. The vast distances between Earth and other planets or cosmic bodies make communication challenging. Signals can take anywhere from a few minutes to hours to travel between Earth and other planets. 2. Signal strength. Signals weaken with distance, making it essential to use powerful transmitters and sensitive receivers. 3. Interference. Radio frequency interference, RFI, and other forms of electromagnetic interference can affect signal quality. Spacecraft communication systems. Spacecraft use transceivers to transmit and receive data. These systems are designed to operate in the harsh conditions of space. Spacecraft also use antennas to transmit and receive signals. The size and type of antenna depend on the mission requirements and the distance from Earth. They often store data on board and transmit it to Earth when possible. The NASA's Deep Space Network has supported numerous space missions, including the Voyager and Mars Curiosity rover missions. NASA's Mars rovers and landers use radio waves to communicate with Earth through the DSN. Space probes like Voyager 1 and 2 use radio waves to communicate with Earth. The communication systems used in space exploration are designed to overcome the challenges of distance, signal strength, and interference. These systems enable scientists to receive valuable data from spacecraft and other celestial bodies, advancing our understanding of the universe.